Hello class, my name is Jose Cuevas and I'm going to be explaining modules 8.1 and 8.2 of our Chemistry 1405 class, which consists of explaining the Bronsted-Lowry bases and acids, and also the Arrhenius bases and acids, as well as explaining the meaning of pH and pOH and how the calculations and indicators work. Okay, I'm going to start off by giving you guys some definitions of what the Bronsted-Lowry acids and bases are. So a Bronsted-Lowry acid is any species that can donate a proton to another molecule, and the Bronsted-Lowry base is any species that can receive a proton from another molecule. So one of them is a proton donor, the other one is a proton acceptor. The Bronsted-Lowry theory was named after Danish chemist Johannes Bronsted and English chemist Thomas Lowry. That's where the name Bronsted-Lowry comes from the conjugation of both of the chemists that proposed. The definition for Arrhenius acids and bases pretty much gets covered by the definition of the Bronsted-Lowry acids and bases. It's still the same situation. The acid is going to be the proton donor, the base is going to be a proton acceptor. The only main difference is that when it comes to Arrhenius solutions, it's exclusive to aqueous solutions. Bronsted-Lowry could be any molecule, but with Arrhenius, it's got to be an aqueous solution. For example, let's look at the way that water dissociates, and this also explains why water is a neutral substance, because it's composed by both a proton donor and a proton acceptor. So it depends on what the substance that water is being dissolved with, that it's going to react as either one or the other. And this example also conveys how water is going to act as either an acid or a base depending on what it's being mixed with, because in this case it's being mixed with a strong acid, which is hydrochloric acid. So you have your proton donor already over here, which is going to make your H2O the proton acceptor. Let's move on a little bit and start talking about pH. pH is going to be the measurement of how acidic or basic an aqueous solution is by giving a numeric value to it. It's measured in a scale that goes from 1 to 14, with 7 being the midpoint. And that 14 is always going to be added up from the pH plus the pOH. They're always going to equal 14. So that's the way that you can play back and forth, finding the pOH or the pH of a substance to find each other. I was mentioning how water is a neutral substance. So it's easy to guess that if you have a scale from 1 to 14, with 7 being your middle point, your neutral ground, water is going to have a pH of 7. And to determine if a substance is an acid or a base, you're gonna go based off of that 7. Anything below that 7 is going to be an acid. Anything above that 7 is going to be a base. Okay, so the pH scale, it's a logarithmic scale. So the formula that you need to find the pH of a substance, it's also a logarithmic function, which is pH equals negative log of H plus. And it's a negative log because this lowercase p right here usually indicates a negative log of base 10, which a lot of people leave the base 10 out just as an abbreviation. So to find the hydrogen ion concentration of it, you would have to use it as a negative log, not a positive. And the same case is going to be for your pOH. Whenever you want to find the pOH of a substance, it's going to be the same function. pOH equals negative log of OH, of course. And whenever you find one, you can find the other easily based on the formula that I mentioned earlier, which is pH plus pOH. It's always going to equal 14. If you were to have the pH of something and you wanted to find the pOH, all you have to do is subtract whichever one you have from the 14. Let's say you have a substance with a pH of 12. And you want to find the pOH. pOH is going to be your 14 minus 12. pOH of the substance would be 2. Okay, let's work out this example of calculating the pH of a strong base solution. We're gonna be dealing with a solution of 1 liter that had 1 mole of sodium hydroxide. Usually you would be required to find the molar concentration of it, but let's say that they already gave it to us and we have a molar concentration of 1.0 times 10 to the negative 3. We want to find the pH, but this is a base, so we're also gonna have to be dealing with the OH first. First, we're gonna have to dissociate your sodium hydroxide, and you're gonna end up with this. And whenever this balance equation ends like this, it's telling us that every mole of NaOH produces 1 mole of that OH in any aqueous solution. And what does this mean? That helps us figure out the concentration of OH, because if every mole is going to give us 1 mole of the OH, that means that the 1.0 times 10 to the negative 3 is also going to be our OH. And that's going to benefit us to find the POH. So now to find the POH, all we have to do is go back to our logarithmic formula and plug in our numbers, which would be POH equals negative log of the 1.0 times 10 to the negative 3. And you just have to plug that in your scientific calculator, and you would end up with 3.0 as the result. So that's going to be our POH. And remember what we said on how the pH plus the POH are always going to equal 14. So if you want to find your pH, you're going to have to subtract the POH on this other side just to balance it out, which would leave us with a pH of 11. There's other simpler ways to find the pH of a substance, but it is not as precise since it's just like a visual thing. But there is things like this, your pH strips. You just put them on your substance and it's gonna change the color of the strip depending on where it finds itself on the pH scale. Or there's also a universal liquid that you can put a couple droplets into your substance and it will do the same thing. It's gonna change the substance color into the color that corresponds to its pH levels. But like I said, the accuracy of it, it's a little bit less than your mathematical way to find it, since all you got to trust is your eyes to base it off on that scale. So yeah, I hope you guys enjoy the video.